this is going to be my setup for teaching physical chemistry. I'll break these down, these chapters down into various topics, talking about the Pearson book of thermodynamics by Engel, and so we're going to start right where we'd be in class, chapter 6. Share screen, go to our, try to work this through as best I can. Okay, so chapter 6 is the chemical equilibrium, which is where we're starting to actually get into a lot more of the chemistry and less of the thermodynamics. At this chapter, there's going to be a lot of thought processes that are a little bit difficult. It's hard. We'll try to work our way through it as easily as we can. It's not always going to be the most easy. But a good thing to start off with is, if you are new to this, if you want something to help refresh this, I'd say go back to the chapter 20 in most general chemistry books, which is our thermodynamics and chemical equilibrium, are where we first introduced delta S and delta G. So reminder of all that will help you refresh up the concepts we're going to talk about here. So we're going to introduce some new variables. Some of them are concepts we've already had that we never really put a variable to, never tried to quantify. We always said, oh, reaction's going to go forward. We're not going to worry about putting a variable, but physical chemistry, we have a variable for everything. And we're going to look at some other equations that we had before and increase the complexity a bit. I'll try to make this as easy as we can, but it's physical chemistry. Calm down. It's like, brace yourself, I'm going in dry. So, last chapter we talked about spontaneity, the idea that if you look at the entropy of the system and you add the entropy of the surroundings, it's always going to be greater than 0 for a spontaneous reaction, a reaction that goes without any external force. In this chapter, we're going to derive 2 new state functions from that state. So the first thing we need to remember is that because this how temperature with a changing entropy is greater than or equal to than the changing heat. We already previously discussed that in class, and remember that for our changing internal energy, that's equal to the changing heat and the changing work, the differentials of those two. So that we can put in there that if we exchange the differential for heat for differential for internal energy minus the differential of work. So with that in mind, when we think about this work can be from any sources. Electrical work, it's probably the most common. Expansion of volume, if we're dealing with gases. Expansion of surface area, like a bubble. Stretching, like a spring. But we can separate the work, and if we can separate these works into 2 types. The expansion work, which is our P delta V, and the non-expansion work, which is our like electrical work. So saying we can break down our differential of work as the 2 different types. So why do we need 2 new state functions? Well, we want to be able to think of spontaneity outside of just an isolated system. We want to think of what's the overall spontaneity of something, or what's the spontaneity in the surroundings, or so we're going to look at a way to quantify this in a different, easier way. We're always going to try to make things easier, but with PChem it always seems to work the opposite. So rearranging the previous equation, so we get the change in internal energy to the other side, and we break down our work into the expansion work and the non-expansion work. Otherwise, so we can take that, pull the differential out, so differential of U minus TS, and we divide it by a -1 to get that, to switch the sign there. If we divide by a -1, we flip that, the sign of the greater than or less than sign. Divide both sides, so those become positive as well. So saying that how the internal energy minus our temperature and entropy is always going to be less than or equal to the amount of work that could be done for an isothermal process, where we say temperature is constant. Why is that have to be isothermal? It's because we didn't have a changing T in this system. And that's where we get our first state function. We look at Helmholtz energy, which is A. We say that the Helmholtz energy is equal to the internal energy minus Ts. Also, we could say that changing Helmholtz energy is always less than the work, the total work. So now this statement is particularly useful as it allows us to calculate what is the maximum amount of work possible for any isothermal process, such as a chemical reaction, so long as we know the internal energy, the temperature, and the entropy. So it allows us to say, well, what's the most amount of work we can get out of this? If we do this reaction, how much energy, what's the max amount we can get? Because the Helmholtz energy is always going to be less than, is going to be always less than or equal to this work. If we get all of it out, good bats. This is a perfectly efficient system, but we're always going to be equal to or less than. It's going to limit how much work we can get. So far, we just thought about Helmholtz energy at a constant temperature. But what do we do at a constant volume? At a constant volume, remember we have work that's expansion work and work that is non-expansion work. At a constant volume, expansion work goes away. So if that's the case, no expansion work, we can say that Helmholtz energy must be equal to, less than or equal to the non-expansion work, thus the electrical circuit. Now, if we set it up so there is no non-expansion work, say there's no electronics going on, there's no circuit, there's no way to extract any electrical work, then all types of work have gone away. And so that we say that Helmholtz energy is always less than zero, less than or equal to zero at a constant temperature and a constant volume. So that will look like our next state function. Just note the requirements. That's temperature and volume. Next state function, you should have heard of it if you've been through general chemistry. We'll use this way more widely, but because we typically look at constant pressure rather than constant volume. And that's our Gibbs energy. Using our same equation, our du minus Ts equals negative P delta V plus d work non-expansion. We could flip that P delta V to the other side. And U plus P delta V becomes entropy. And when we say pressure is constant, let's say under constant pressure, that comes entropy, and we have dH minus Ts is equal to, or less than or equal to, the non-expansion work. This is our Gibbs energy, our delta G. Once again, if we set this up so work is, there's no circuits, there's no way to transfer and extract electrical energy, we say that delta G is less than or equal to zero. So these are spontaneous systems at either constant volume and temperature or constant pressure and temperature. Now, why is this simpler than just thinking about entropy? Well, look at this equation. We have delta S minus delta Q over T. It's greater than or equal to 0, otherwise known as delta S plus delta S surroundings. Isn't this sufficient? Well, nothing really changes when we look at G and A in regards to looking at the spontaneity. But with G and A, we no longer have to explicitly consider the surroundings. We no longer have to classify the surroundings as a separate region to worry about. We can now just look at the system. What is the entropy of the system? What is the enthalpy of the system? Rather than have to worry about what is going on in the surroundings. So it helps us limit our focus, make this a little bit easier to deal with. And because of how we just set this up, it allows us to calculate the maximum non-expansion work for a given reaction. So how much electrical energy would we get from a 100% efficient system? So what is the maximum amount of work on a per gram basis between methane and ethanol at 298.15 degrees Kelvin? So hypothetically, we're saying how much can we do this? If delta A is equal to delta H of the reaction minus nRT, which is our changing volume, which is our PV, that gives us our internal energy. How do we get internal energy? Well, it's delta H plus PV, so negative P delta V. So calculate that. Now, unfortunately, I don't have my book in front of me, so we'll have to click forward. These numbers you could all look up, and this part's not super hard. We go that, how would we calculate the heat of combustion of this? Well, you'd look up the values. You'd say, CO2 is 285.8. Well, that's water times 2. And CO2 is 393.5. And we subtract our delta H of our reactants. 2 oxygens, but those are 0. And methane, which is 74.6. So you get 890.5. You do that with ethanol, you get a larger number. Fine. Now, when we go to calculate our nRT, we look at how many moles of gas we have changing. We only want to consider the moles of gas, so not the liquid. So CO2 is 1 mole of gas, and we came from 3 moles of gas. So we have a net change of -2. We'll use our R as 8.314 joules per mole Kelvin and our temperature to get this into joules. Then we'll have to convert that into kilojoules. Our temperature is 298. In case of ethanol plus 3 oxygens, that's 3 gases. There's 2 gases. That's a net change of -1. So we're going to see a slight difference. And of course, our delta S, we can calculate that. We can look that up. So delta S, same thing. We're going to subtract those. We find those numbers. We're just going to plug these in. So you calculate that. You get what the delta A for methane is 813. Delta A of ethanol is -320.1323, but that's per mole. If I want to do this on a per gram basis to see which one of these is going to be able to produce more energy, we have to turn moles into grams. So looking at this, we're going to need to multiply by the molar mass of methane. Methane is 12 plus 16 grams per mole, while ethanol is times 2 plus 6 plus 16 46 grams, much heavier. And so you get that on a per gram basis by weight, you could get more energy from burning, more like work from burning methane than you would from ethanol. Even though ethanol produces more, you need more of it to get that same effect. So, some thoughts of this. While non-expansion work is always more efficient than work via heat-mediated expansion. So, if optimized, it could generate 100% efficiency, which is why all these cars want to go to using fuel cells. Because if you can get energy out of fuel cell, you're not going to be losing so much energy as heat, and thus losing a lot of your energy you're producing. So, but because of the delta G equals delta H minus T delta S, we can make a few bold predictions. And this is something we've done before. If the reaction is exothermic and entropy is increasing, it will be spontaneous at all temperatures. If the reaction is endothermic and entropy decreases, it should be non-spontaneous at all temperatures, meaning it will not go by itself. Entropy has a larger effect at higher temperatures, and we can use the size of delta H and T delta S to determine whether it's spontaneous or not. That seems the simplest statements we could actually make, considering this is PChem we're talking about. Now, these next few proofs are going to cause excessive eye twitching, but this is going to be useful down the road. This is going to allow us to exchange hard stuff and turn it into easy stuff. We can use these to break down and exchange and find out how to look at U and how a bunch of different reactions. Now, I have 1A, 2A, 3A, 4A, because each one is looking at a different setup. But we can follow 1A to 2A to 3A to 4A or whatever. I say 1A to 1B to 1C and 1D. And all those are going to be interlinked. So 1A is just looking at something we know, that internal energy is equal to TdS, that is our heat, and PdV. So it's turning the non-state function heat and non-state function work into state functions or state variables, T and S and P and V. If I look the same thing with enthalpy being internal energy plus PV. So we can exchange the PV and PV, they cancel out, and so we get VdP. So volume at a changing pressure. So this is just exchanging what we know for internal energy to get enthalpy. And we just learned about Gibbs and Helmholtz, so we can get that, oh, okay, if Helmholtz is, if we look at the changing TD, T and S, we get TDS and SDT. So plugging that in for Helmholtz, which is the internal energy minus TDS, or the change in TDS, we get that Helmholtz is our work, and our minus SDT. Same thing with Gibbs. You see the SDT again, but now it's VdP because it's based on enthalpy. So take a minute, soak this in. So we have right now some equations I've highlighted in bold, equations we actually need to look at. We have some statements of these variables U, H, A, and G in terms of state variables. So what does that mean? Means our internal energy is a function of entropy and volume. Our enthalpy is a function of entropy and pressure. Our Helmholtz is a function of temperature and volume, and our Gibbs is a function of temperature and pressure. These are called a function's natural variables, meaning that this is going to be how we look at these guys. Now, if we differentiate the variables with respect to each of these variables, we can say that du ds at a constant v is going to be t. So basically, that part, constant volume, that part drops out, and we're left with just t. I'm just dividing both sides by dx. And if I divide by v at a constant entropy, we get negative p. So looking at how does internal energy change with volume when entropy is not changing. You say, well, that's equal to whatever the negative pressure is. Same thing with enthalpy. Same thing, so you get positive V when changing pressure. Looking at how does Helmholtz change with temperature at a constant volume, negative entropy. How does Helmholtz change with volume at constant temperature? You get negative pressure. So you see some similarities between 3 and 4 and 1 and 3, or 2 and 4. Now, those are some exchangeable state functions, exchangeable relationships, exchangeable differentials. Now, because of all these are state functions, by definition, a state function means it's path independent. If you differentiate it based on two different variables in different orders, it will give you the same result. We did this with pressure. If we look at pressure and we differentiate pressure with respect to temperature and then volume, or volume then temperature, you'll get the same result. So we can have this Maxwell relationship for all of our things: our internal energy, our enthalpy, our Helmholtz, and our Gibbs. So we say, oh, if I look at changing entropy, changing volume, versus changing volume and changing entropy, well, I'm exchanging what was our changing entropy. Our entropy was temperature, and our changing volume was negative pressure. So we get this, what's called a Maxwell relationship, saying that we can't find this one directly just yet, but we have that this crazy thing. How does temperatures change with changing volume when you hold entropy the same? Well, that's equal to negative of the changing pressure versus changing entropy. Temperature changes as a function of volume at a constant entropy, same way that pressure, in an inverse relationship, the pressure changing at a changing entropy at constant volume. So we're plugging this in, what we just found in step B, and then carrying it through. The T goes up there, the E goes up there. So we have these Maxwell relationships. That means we can look at a difficult concept and exchange it for something easier. Especially here in 3C and 4C, we get looking at how entropy changes with volume at a constant temperature, and is related to how pressure changes with temperature at a constant volume. Now, for a real thing, we found this differential earlier. Not today, but earlier in the class, that pressure and temperature can be exchanged. This exact differential can be exchanged for the thermal expansion coefficient and how pressure will expand on a solid. I'm trying to think. How volume will expand when heated, and how pressure will expand under heat if it's not allowed to move. The same thing here. We get we're going to say look at how entropy and pressure changes, or we can exchange this for something, how volume, temperature changes at a constant pressure. How does volume change constant temperature? We found that to be beta times volume. So we have these Maxwell relationships what we can exchange. Finally, essentially, these Maxwell relationships will allow us to exchange obscure derivatives that we don't know how to find with something that we can find. And that's what we're going to be using. Now, the crucial note on what it means to be at a constant entropy. When we have a constant entropy, where the S is down here, the process is a reversible adiabatic process, because constant entropy, so our change in entropy is equal to changing heat over temperature. So the only way changing entropy is zero is if heat would be zero, and heat is only zero for adiabatic process. So we're saying, how does temperature change with respect to volume under an adiabatic process? Well, that would be equal to how pressure changes with entropy under an isochoric system. That'd be inverse. So the final thing we'll talk about before we end for this little video is why the dependence of G and A on T, P, or V. So we'll spend most of the time with Gibbs, but because we use a lot of constant pressure chemical reactions that occur under like atmospheric conditions. But so still don't want to forget about A. So let's think about these partial differentials. So A and G from 3B and 4B. That's saying that, well, if I hold volume to be equal to zero, change volume is zero, then the change in temperature is going to be negative entropy. And changing volume, constant temperature is negative pressure. Same thing, negative entropy and volume. So if entropy, pressure, and volume are always positive numbers, what does this mean? It means as temperature and volume increase, as they increase, Helmholtz will always get more negative. That Gibbs will always get more negative as temperature increases, but as pressure increases, it will become more positive. So that should tell you something. That as we change the volume and change the temperature, if the sun expands, Helmholtz would go up. If something heats up, if volume expands, Helmholtz would become more negative. If temperature increases, Helmholtz gets more negative. As Gibbs increases, Gibbs will go more negative as temperature goes up. And if we increase the pressure of our system, it would go down and essentially become less spontaneous. So we'll think about that in the near future when we start to worry about these variables. Okay, we're going to stop there. So this gives you something to think about. We've introduced our Helmholtz and our Gibbs, and in the next chapter we'll start, and the next little bit, we'll start to look at how do we actually start calculating for delta G. So this has been a little bit something to think about. Let's worry about this, and we'll keep on keeping on. See you in the future, Cowboys.